there's no.
So it's a great pleasure to introduce Marc, who is visiting us until the end of next week. He is no stranger to Dublin, having spent some time here. So right now he's based at the University of Leipzig in Germany. So among many other things, Marc has done pioneering work on green functions in black hole spacetimes. And this is the topic that he's going to tell us about today. Yes.
Okay, so good afternoon, and thank you very much for inviting me to give a talk, particularly to Yasaman. So yeah, so like Yasaman has said, I'll be talking about green functions. This is it's really a Yasaman dedicated talk because I've done a lot of work on green functions with applications to different areas in physics. So in this talk, I've put it all together. So there's a bit of a mishmash. The common factor is green functions, and I'll be talking about applications to different physical settings. There's relationships between the different settings, but I'll make sure that I make it clear as I move on to a new setting. The common thing is green functions. This is for black hole space-time perturbations. So this is really what I'm doing all the time. We have a background black hole space-time. We perturb it with a field, with a linear field, and we look at the wave equation that it satisfies. We solve for that wave equation, and then we can do physics with it. We can do classical physics. We can do quantum physics. So these are the different. These are layout of the talk. So first of all, I introduce black hole perturbations. Then I will be talking about one of the first applications of green functions, which is essentially the cell force problem for extreme mass ratios spirals. Then I'll talk about black hole stability properties. It will be two subsections. One will be extremal black holes, and the other one will be the Cauchy horizon of black holes, so inside black holes. So 2 and 3 are classical, it's classical physics. And then the last section is quantum physics. It will be two subsections as well. The first one is going to be communication between particle detectors and then entanglement harvesting. And feel free to ask questions at any stage. So, okay, so let's start with black hole perturbations. So this is the Kerr metric. So all astrophysical black holes are expected to be modeled by the Kerr metric. So it models a rotating black hole. It's described by two parameters, the mass m and the angular momentum per unit mass a. And this is the metric here in Boyer-Linkowitz coordinates. There is this delta function here, a function of the radius. These are Boyer-Linkowitz coordinates. They're spherical type coordinates. Delta depends on the radius. It has two roots, r plus and r minus. They correspond, r plus corresponds to the event horizon, and r minus corresponds to the Cauchy horizon. You can see by the formula for the radii of the event horizon, r plus, which is that for a larger than m, the argument of the square root is negative, you have no event horizon. So there's a maximal rotation for the Kerr black hole, it's a equal to m. And for a equals to 0, you've got no rotation, that's the so-called Schwarzschild black hole. And each horizon, r plus and r minus, have got associated angular velocity, omega plus or omega minus, and surface gravity, kappa plus and kappa minus. So this is an exact solution of Einstein equation of general relativity. This is the Penrose diagram corresponding to Kerr. I don't know how you're knowledgeable of Penrose diagrams. Time goes in the vertical direction, essentially radius in the horizontal directions. They're compactified time and radii. And the important thing is that null geodesics, radial null geodesics, radial in quotes because it's Kerr spacetime, are at 45 degrees. So they really tell you about the causal structure of your spacetime. This diamond here is the outside of the black hole. So this is chi plus, this is future null infinity, late times far away, radial infinity. This is chi minus, early times. H minus the past horizon, H plus at R equals R plus in late times, Fourier linkage times, is the future event horizon. The diamond here is the inside of the black hole. And this diagonal here is the event horizon. This other diagonal here is the Cauchy horizon at R equals R minus. So beyond this, there's a tricky region. There's going to be one part of the talk dedicated to that. But beyond this, the metric can be analytically continued. The analytic continuation has a time-like singularity at R equals 0. But there is no unique smooth extension through R equals R minus. You have an infinite amount of smooth extensions. I'll be talking about that at some stage in the middle of the talk. Any questions so far?
So you have chosen one kind of extension
here. So these two diamonds here, just the unique. This diamond here is the unique smooth extension of the outside. This diamond here is the analytic extension. So there is one unique analytic extension. There's many smooth extensions. Here's the maximal, well, not maximal, but analytic extension into that diamond. So for almost the whole of the talk, this diamond will not play any role. At some stage it will, and I'll indicate it.
If you focus on smooth extensions, now the causal structure beyond that can be quite varied.
Yes. So you need not have a time like you can have a smooth extension through the Cauchy horizon, which does not have a time like singularity, for example. Okay, so that's the Penrose diagram of Kerr. I'll be talking mostly about Kerr, but I'll be switching to other little spacetimes, little or big spacetimes later on, Schwarzschild, Kerr, and so on. Okay, so as I said, Kerr is an exact solution of Einstein equations of general relativity. Now, that's what you would have if you had black holes in isolation. In practice, we've got matter in the universe as well. So the black holes are being perturbed by fields, whether classical fields or quantum fields, where scalar field, Feynman field, magnetic field, linear gravitational perturbations, you name it. So you can have classical matter near a black hole that perturbs the black hole. You have accretion disk, neutron star, another black hole that wouldn't be matter, but you would have gravitational perturbations of your bigger background black hole. And you can have also quantum fields, which are always there, the quantum vacuum, there's quantum fluctuations all the time outside the black hole that give rise to the famous Hawking quantum radiation. Okay, so that's what we're going to do. We're going to perturb with fields our some black hole spacetime, and that's modeled by a wave equation. So we consider linear field perturbations of a fixed background black hole spacetime, namely Kerr most of the time. The metric is G mu, and in the case of scalar field perturbations, the scalar field phi obeys a second order hyperbolic linear partial differential equation. It's the Klein-Gordon equation, box of phi equal to some source. This is the specific form of the Klein-Gordon equation in the case of Kerr in Fourier linkage coordinates. Okay, so it's a hyperbolic, second order linear hyperbolic. So this is really what we want to solve for. Now, I wrote it down for scalar fields, for fields of other spins, electromagnetic, neutrino, or gravitational fields. One can write similar equations. So Tikhonsky in 1973 managed to decouple the fields for the different components of the field into one single so-called master Tikhonsky equation. Again, it's a second order linear hyperbolic PDE. The operator, I call it O hat. And the type of field, so I call it by psi. Okay? So mostly, almost all the time I'll be talking about scalar fields, but you can, other fields of other spins obey similar type of equations. Now, the object of main focus for this talk.
Presumably that was done in a particular gauge for the electron.
So this is not the Tucholsky quantity psi. They're particular scalars constructed by basically the field and derivatives of the field in such a way that that quantity is gauge independent. It depends on you choose a tetrad. It depends on the tetrad, but it does not depend on the gauge. So you construct gauge independent quantities. Those are the ones that obey this Tucholsky equation. Not the whole. So it's correct that not all components of the field obey that equation. So there are other components that do, but you can combine certain components in such a way that they're gauge independent and they satisfy the Tucholsky equation. So the main object of this talk is the Green functions. It's a mathematical object, and we will apply it.
You can't write down the equations for fermions with a gauge with an electromagnetic field.
You can do it for Feynman field perturbations of Kerr and for electromagnetic.
In the absence of an electromagnetic field, the zero electromagnetic field.
Yeah.
Because there's a gauge field that should be in the covariant derivative. Only the connections are set to zero.
Yeah, but that's for a charged. That's for a charged field.
Well, which the fermion is. Electrons are charged.
Yeah.
Presumably for Kerr, the background gauge field is just zero.
Wouldn't you want to consider an electromagnetic field as well? And coupling to an electromagnetic field for QED?
Only if you're considering charged Kerr.
No, if you're considering charged particles in Kerr.
But this would be just for fields, for Feynman fields with no electromagnetic field propagating on Kerr.
Yes, with no magnetic, with no electromagnetic field.
Yeah. So the main mathematical object we're interested in are the Green functions. So they obey the solutions of the Tucholsky equation, but now the source is no longer a physical source. It's a four-dimensional Dirac delta distribution. That's what I call Green function. There is different solutions to this equation depending on what boundary conditions you impose. I'm going to be talking about two particular types of Green functions. One is the retarded Green function. I call it the classical Green function. It satisfies the boundary condition that it's equal to zero if your field point is not in the causal path. Sorry, if the source point is not in the causal path of your field point. So, namely, if you've got a whirl line here and you've got a field point x on this whirl line, you draw null geodesics. Remember, this is in Kerr spacetime now. They can hit the whirl line again in the past. We'll talk about a lot about this. In the region inside the causal path of x, the Green function can have support and be non-zero on the light cone, and inside the light cone it can have support. Outside the light cone, it is zero. Okay, that's your boundary conditions. That's your causal Green function, your retarded Green function, your classical Green function. It's very useful in particular because if you have some initial configuration for your field, for your psi, so you choose some initial hypersurface, give value for the field on that hypersurface, give value for the derivative of the field perpendicular to the hypersurface, then you can use your retarded Green function to evolve it to any time to the future. So you know the value of the field anywhere to the future of your initial hypersurface. So that's a classical one. You can also define a quantum Green function. In particular, you can have a Feynman Green function. It's a propagator. It depends. Now we need to quantize the field. The quantum field now with a hat to denote operator value distribution. It is in some quantum state psi. The Feynman Green function is just minus I times this. It's, as I say, it's a time ordered product. So you've got Heaviside theta in front of the Weidmann function, depending on whether the point x is to the future of the point x prime or vice versa. So that's here now the expectation value of the 2-point function in some quantum state psi. So the first part of the talk will be about classical fields, classical green function, and towards the end I'll talk about the quantum properties and the quantum green function. Okay, so let's talk about the first application of green function, and it's a classical one, so it's wave propagation and cell force. Okay, so wave propagation, I'm going to give you a video here. This is by courtesy of Barry Wardell, sorry, in UCD. So this is Kerr spacetime, this is the equator of Kerr. You've got, so this is a numerical calculation of your green function, where your source is on the equator at r equals 12m in Kerr spacetime, and as a function of your field point, so you're still on the equator, and you've got all these different field points on the equator, and as time evolves. So you can see your black hole here in the middle, and then you have a dot here, which is where the initial impulse is. You can think of the green function of the value of the field due to an infinite impulse at one particular point in space-time. So that's where that impulse happens, and then the field just propagates. Okay, I'm going to try to. So there's a lot of interesting stuff going on here. So first of all, you've got a wavefront. So on the horizontal axis, you've got the value of the green function, the value of the field. So in here, it's a highly peaked. It actually would be exactly divergent. Okay, I'll tell you now analytically what the divergence is like. Numerically, it's just very highly peaked. It's a very large value. That's just the value. That's just the wavefront, the null wavefront. That's just where the null geodesics are. So the null, the field is just propagating mostly on the null wavefront.
And we didn't specify the angular momentum of Kerr here.
Oh, I can't remember, 0.7-ish.
So it is rotating.
It is rotating, and in fact, good point. So you're going to see this in a second. You're going to see how there's a dragging of frames. You see how the wavefront is going to be dragged. You'll be able to tell in which direction the Kerr black hole is rotating. Now, it's not rotating fast enough to be able to tell, but you will be able to tell in a minute. So far, it's flat space-time-ish, okay? All you see is this part of the wavefront is being absorbed into the black hole. The other part is just propagating flat space-time-ishly. Okay, in here, though, the part that's getting close to the black hole is actually it's going to start orbiting around the black hole. You're really seeing the orbiting null geodesics. This wavefront is really following the null geodesics around Kerr. So now you see how this wavefront here has gone around here and passed the line on the antipolar line, so the antipolar line, and another wavefront that's going this direction, and they've just crossed. The place where they've crossed are caustics, by the way. I'll be talking about caustics later on, and it has consequences for physics. Okay, so now the wavefronts have crossed, and they continue to orbit around. So you can see now, this is where the two wavefronts are meeting, so they're not in the antipolar line. You can see how the rotation of the black hole is dragging the frames. Okay, so this continues happening, and in fact this happens an infinite amount of times, an infinite amount of orbiting of null geodesics, just the magnitude of the field is decreasing. I'll tell you now analytically how we can model this. So that's what the green function for a scalar field in Kerr spacetime looks like, a numerical calculation of it and approximation to it. So you can see here a lot of features of wave propagation around the black hole spacetime. So let's look at more in detail into some of this, particularly with an application to the cell force problem. So this is for modeling extreme mass ratio black hole inspirals. So you have a massive black hole of the order of 10 to the 5, 10 to the 9 solar masses, and a small black hole in relation to that one, which is of the order of 10 solar masses, orbiting around it. In that extreme mass ratio limit, you can use black hole perturbation theory. Okay, it's very natural to use black hole perturbation theory. And what happens is the small mass has a gravitational field. Which acts upon itself. That's a cell field, and so it exerts a force upon itself. It's so-called gravitational cell force. Of course, the field, if you calculate of the particle of the mass, if you calculate the mass itself, it's going to be divergent in principle. So you need to regularize it in an appropriate manner. But essentially, you can model your full space-time as some background metric of the massive black hole, plus a perturbation due to the smaller black hole. That's the linear order in the ratio of the masses, and you can go to higher order in the mass ratio. So this is an expansion that's valid far away from the small mass, and really far away from the inspiral. That gives rise to the gravitational waves, which could eventually be observed in Earth. Indeed, LIGO has detected gravitational waves from black hole spirals, not in the extreme mass ratio limit. There's going to be the laser interferometer gravitational space antenna, which was just accepted by LISA. Now it's adopted by ESA just a month ago, and that's planned to launch in 2035. And that's going to be one of the main sources of gravitational waves are going to be extreme mass ratio inspirals, which can be modeled using perturbation theory and the gravitational cell force. So the smaller mass deviates from a geodesic of the background spacetime due to the cell force. Okay, now, so that's for a gravitational cell force. You can also calculate the cell force due to scalar charge propagating in Kerr spacetime. The scalar charge creates a scalar field which can act upon itself. It creates, you need to regularize that. It creates a cell force. And that's an expression with which you can calculate the cell force of the scalar cell force. And it's a derivative, a covariant derivative of a Ward-line integral of the retarded green function. So the green function is a pi function. It depends on two spacetime points. One is the field point where you evaluate the cell force. The other one is the integration you integrate along the past Ward line of the charge. So the retarded green function is useful for calculating the cell force. And there's a similar, although more complicated expression for the gravitational cell force case. You can have an electromagnetic cell force case as well if you have electrical charge. I'm just going to be talking about the scalar cell force now. So how does the contribution to this this is a very non-local integral, you calculate the value of the cell force at one space-time point, and that will be due to the whole past Ward line of the charge. Okay, this does not happen in flat spacetime. You do not have these non-local contributions in flat spacetime. That's a very particular feature of Kerr spacetime, as I'm going to show you now. So how does this arise? Well, there's going to be mainly two contributions. One is the backscattering of waves. So this is an analytic expression for the retarded green function. This is the so-called Hadamard form. It makes explicit the singular structure of the retarded green function. So that's a very powerful expression. The caveat is that it's only valid in a normal neighborhood of the point. Okay, so only very locally, only when there's a unique geodesic joining the two spacetime points. So if you look at this form, it's got a theta delta t, just tells you it only has support in the causal path. Sorry, not in the causal path, in the path of x. Remember, there's a retarded green function multiplied by something which has support on in the light constant. That's delta sigma. That's a direct delta distribution whose argument is sigma. Sigma is the Ward function, Singh's Ward function, Singh being a professor in dyades. So This has support only whenever sigma is equal to 0. Sigma is equal to 0 whenever the points are separated by, they're null separated, they're light-like separated. It's multiplied by a regular by tensor. This is the square root of the Van Blank determinant. And then there's another term here that has support whenever sigma is negative. Sigma is negative whenever the two spacetime points are time-like related. So this is again a cartoonistic depiction of it. The first term has support in the light cone, the red line, sigma equals 0. The second term has support on the green region that's in time-like paths. So this is due to the backscattering of waves. V, the coefficient of theta, this backscattering by tensor, is equal to 0 in flat spacetime for massless fields in flat spacetime, and it's not equal to 0 for massive fields. In Kerr spacetime, even for massless fields, it is not equal to 0, so you've got backscattering of waves. So before in the previous video, when there was the null wavefront propagation, there was actually non-zero value of the green function in between wavefronts. It was just too low to be able to see it, but that was due to backscattering of waves. So that's one important contribution to the green function in the Warline integral for the cell force. Another one is the one that you saw in the video, is the one due to the orbiting null geodesics. So this is not the direct null geodesic. The direct null geodesic just goes away, propagates all the way to radial infinity. But the ones that orbit around, they're already in the causal path. They're inside the causal path. So these points, say you fix a point here, and then you take this your field point, and then your source point, you just go around a circle, a time-like circular geodesic in Schwarzschild spacetime.
Just I was thinking about your previous experiment. The leading term there, that's Huygens principles, isn't it?
There's violation. There's
No, the delta.
yeah, that's right. That's yeah. So
it's only true in even dimensions. That form.
Yeah, so there's equivalent Hadamard forms for
For
other dimensions, and then you've got it's not no longer delta sigma. It changes.
So what are the green curves then?
Yeah. So here, okay. So what's here? So we fix a point here, x here, and then we vary the other point. The other point, the black line here, is a time-like circular geodesic at r equals 6m in Schwarzschild. So what are these colorful lines? These are null geodesics emanating from this point. So the null geodesic, the red line is a null geodesic going in this direction, emanating from x, going like this, and then hitting the time-like war line here. So these two space-time points, x1 and x, are joined by two geodesics. One is the time-like circular geodesic, like here, and the other one is a null geodesic going around this way.
And so, how do I understand your remark about the, I don't know what color it is, brown, is it?
This one here?
Yeah.
So then you can play the same game with null geodesics that orbit around the black hole more times.
Yeah.
So the next one, I think it's the blue one. So the blue one does like this. It orbits all around the black hole, and it goes back and it hits the circular time-like geodesic again somewhere else along that geodesic.
After a finite number of loops or what?
It just goes around the black hole like this.
So it goes around twice?
It goes around 360 degrees plus almost pi
So
again.
1 and a bit times.
Yeah. And then the next one would be the orange one. I think it does like this. And the next one would be the green one like this. And then you can just keep doing this again an infinite number of times, because in fact there is the asymptote to the unstable photon orbit at r equals 3m. So what are the contributions?
So that's the line here to 3m. And the outside is 6m.
Yeah, so 3, exactly. So 6m is this time-like circular geodesic here. 3m, you're right, is this one here. You can't really see it because it's almost overlapping with the green line, because they're asymptoting the 3m. They're getting closer and closer. The more orbits they do, the closer they get to the unstable photon orbit.
How can I see that that ratio 6/3 is 2? How does that, is that easy to see?
We picked 6M. We could have chosen another. You can choose a different radius.
But then the inner one would be what?
3M is always 3M. The unstable photon orbit is always a 3M.
Oh, yes.
And we've chosen.
Oh, yeah. So you could have 10M and then 3M.
Exactly, yeah. Yeah. Okay, so this is what brings about the contribution to the cell force. You've got all this does not happen in flat spacetime. All these contributions coming from the backscattering of waves, from V, the tail, the Hadamard tail V being non-zero, and also from all these orbiting null geodesics. Okay, so this is an actual plot of the calculation of the green function that I did with collaborators, Sam Dolan and well. There's I'm mixing a lot of words here, but this is mainly the people in UCD, Adrian Oswell, Sam Dolan, Barry Bordell. A calculation of the green function of the function of time, and you can see here the divergences. So this is the 1/sigma is the okay. So there's no direct. The Hadamard form here is no longer valid. We're outside the normal neighborhood. We're beyond the normal neighborhood. So we proved, it's been shown in many different ways, that after the delta sigma, the green function is still divergent whenever the 2 points are connected by a null geodesic, even outside the normal neighborhood. That's been shown in the past. That's known from Hormander's work in PDEs. What we showed is what the singularity structure is. So at the first light crossing, it's 1/sigma. After 2 light crossings, it's minus delta sigma. Then it goes to minus 1/sigma, and then it starts the whole cycle again. Delta sigma, 1/sigma, and so on. It depends on how many caustics the light, the null wavefront has gone around. Every time it goes around one caustic, and it hits the war line again, the time-like war line again, it changes from one type of singularity to another type of singularity. So that's been shown in many ways, and you can see here in numerical calculation a 1/sigma type of singularity, a minus delta sigma type of singularity. So the 1/sigma will correspond to this light crossing here. The next one is the orange one. So it does like this, it goes around 2 caustics, and it has when it hits the war line, it has a minus 1/sigma type of singularity, and then delta sigma and so on. Okay, so this is the green function. We want to calculate the cell force. So what we need to do is integrate this war line, differentiate it with respect to r or angle or whatever it is, depending on the component of the cell force, and then you calculate it. So there's a plot of different components, the time component, the radial component of the cell force. This is for eccentric orbits, not for circular orbits, as a function of the eccentricity. Okay, this is a plot just to show you how a useful calculation of the green function as an application to the cell force. Sorry, Yasmin, how am I doing for time? Right?
Fine.
Fine.
Yeah.
How much have I got left?
We don't have hard cutoffs, so, yeah.
Okay. So that's the first application of the cell force, of the green functions. The second one is black hole stability. So as I say, I'm going to be talking about many different settings and many different results that I've obtained throughout my career in different stages with different groups. All of them have in common applications of green functions. So the next one is black hole stability. This is classical black hole stability. So for this, we're using mathematical techniques before we use the Hadamard form and other techniques. In here, we're going to do Fourier analysis. We're going to do complex analysis. So we'll apply a Fourier multi-composition of the green function, and we'll apply it to 2 different things. One is going to be the modeling of the late stage of a gravitational waveform for any type of black hole in spiral, not just for embryos, not just for extreme mass ratio black hole in spirals, even for the ones that LIGO detected. So I'll tell you about this in a second. The second type is going to be the stability of black holes. And in particular, I'll look at extremal black holes and also Cauchy horizon of black holes in the Cedarr universe. So, okay, what do we do mathematically? So a couple of slides of mathematics. With the Fourier mode decomposition, and we also split into spheroidal harmonics. So you've got your Fourier integral along the real axis here, spheroidal harmonics here, your standard harmonics in the azimuthal coordinate here, and your time factor, exponential factor here. The factor here, these are the Fourier modes, they just depend on the radii, R and R prime. These really, the Fourier modes really carry most of the physics of the problem.
What is theta?
Theta is the polar angle.
So you just have one variable there.
What do you mean one variable? You've got, so G red is so the green function is a function of two spacetime points and x and x prime. So it depends on the coordinates of both x and x prime. The coordinate theta of x is here, the coordinate phi of x is here, the coordinate t of x is here, the coordinate of r of x is here, and the same thing for the x prime, phi prime, t prime, theta prime, r prime.
Yeah, I see that. But so then
He could have absorbed
what is
each of
the
the
spheroidal
into
harmonic?
the spherical harmonics.
So spheroidal harmonics are, so you know that your spherical harmonics, so if you're at an oblateness to your sphere, that's what the spheroidal are. These are in fact screen-weighted spheroidal harmonics. If you're
Oh, so it's just when the sphere is not the sphere.
yeah, it's a plate or prolate.
Yeah, okay.
Yeah, because this is Kerr. Remember, we're in Kerr now.
No, I think I've seen that.
So it's true that it keeps switching a little bit between Kerr and Schwarzschild and so on. So here, going back to Kerr, I'll stick to Kerr as much as I can, but sometimes I'll deviate from it. So this is Kerr.
This is just the generic expansion of
Yeah.
one function in polar coordinates in time.
Yeah, so as long as you have yours, any black hole spacetime will satisfy this. So in the case of A equals your Schwarzschild, this would just be the spheroidal harmonics just reduced to spherical harmonics. So your Fourier modes, GL omegas. Okay, so why do we do this? Well, one big advantage is we've started off with a four-dimensional PDE. We've reduced this to an ODE. Now the Fourier modes satisfy a second-order linear ODE. It's a radial ODE in the radial direction, and there are green functions. They're just unidimensional green functions. So they're much easier to calculate. Of course, solving an ODE is much easier to do than solving a PDE. So now we can go back to our books from undergrad. We've got an ODE, a green function for an ODE. So how do you get this? Well, you find two real independent homogeneous solutions. I call them R in and R up. They're homogeneous solutions. You evaluate them, so you need to choose them with the right boundary conditions. You evaluate them at two different space-time points, the smaller radius and the larger radius, and you divide them by the Bronsky of the two solutions. In here, we're calculating the retargeting function. So we're still in classical physics, we're calculating the retargeting function. So the ones that satisfy causal boundary conditions, or the ingoing, that one is evaluated at the smaller radius. So there's nothing coming in. It will never be evaluated at sky minus, because it's always, the argument is at the smallest radius. So it's purely going waves into the horizon and purely going to infinity. The upgoing one, that's the one whose argument is the largest radius, so it will never be evaluated at the horizon. It's the one that has purely going waves to sky plus and purely ingoing to H plus. So these are the boundary conditions for your modes, green function modes, that will give rise to the retarded green function, the one that satisfies the causal boundary conditions.
Why don't you have two terms on the right side? I mean, the
Here?
classical green function.
Sorry, the terms
It
in.
really is what I think it is. It's you need another. You need to know whether R thing we've got R less and it's bigger than R greater. There should be two terms there, shouldn't there?
Sorry, what do you mean the terms? There's two factors. One is evaluated the smaller radius, the other one is evaluated the larger radius.
You're thinking of the
It's
same
continuous.
thing.
It's not going to give me a delta function.
It is, because because one is the larger radius. This is effectively a heaviside theta. You can rewrite this as a heaviside theta of R1 is R primed, R in R, R up R times R in R primed, plus theta R prime minus R
Oh, yeah.
of.
Yeah, if you write this as something, okay. I believe you now.
Thanks. So, okay, so we're not staying here. So we've got the Fourier integral around the real axis. Now we're going to go into the complex frequency plane. So we're going to deform the contour into the complex frequency plane, and we're going to apply the residue theorem of complex analysis to pick up, to sweep off the singularities of the Fourier modes. So this is not an exact calculation, it's just a depiction of the singularities of the Fourier modes. So this is the complex frequency plane. Every time I say the Fourier integral is around the real axis, really is just slightly above the real axis. So that's where your Fourier integration would be. And what we want to do for the retarded green function, what we are going to do is, we're going to close the contour by going down the lower plane. And so by doing that, we pick up three contributions. One is the high frequency arc that closes the contour. Another one is the poles, the simple poles that the green function modes have. And the other one is you can show that the green function modes also have a branch point at the origin. And so there's a branch cut going down the negative imaginary axis. So you want your contour to go infinitesimally close to the negative imaginary axis, go around it, and so on.
That's terrible. I mean, would you not make the branch cut go up to plus infinity instead?
I think you probably could, because none of the physics should depend on the.
No, the mathematics. You could have an easier integral to do.
But he's going to have to deal with it at the other side.
Yeah, you would. Yeah.
I think it's easier to deal like this with you, because now if you had it on the upper plane, I'm not even sure you would have to go.
Are you going to use the upper plane at all?
I'm going to tell you a little bit about it, but I'm not going to use it to calculate the retarded green function. Okay, so the way we're doing it, we've got three contributions from the high frequency arc, from the poles, and from the branch. Now, we're only going to care about the middle one. You can prove that the high frequency arc basically gives a direct null wavefront. It's negligible after the direct null wavefront has gone through. The branch cut, well, it has contributions at many different times. The main contribution really dominates at very late times. So at the end, at very late times, as t goes to infinity, the field decays as a power law tail decay that was proven by Richard Price in the 70s. It contributes before as well, but that's the main contribution. The more interesting bit is the poles. In fact, it's been shown that they give, by Adrian Otwell and Sam Dolan, that they give rise to the fourfold singularity structure that I showed you before. So let's concentrate on the poles. The poles means that the green function modes diverge. So these are at some complex frequencies. And remember the time dependence is exponential of minus I omega t. What does that mean? If you've got poles, if you had poles on the upper plane, that would tell you that at late times, as t goes to infinity, they diverge. They grow exponentially with time. If you've got poles on the lower plane, they just decay exponentially fast with time. So the ones on the upper plane, we call them unstable modes. And the ones on the lower plane, they are the so-called Poisson modes. Okay, so we'll be talking about both types. The first type, this is an actual exact calculation of Poisson modes in Kerr. I did together with Huan Yang and Perimeter Institute, in fact. So this is for particular values of A. As A increases, I want to point to the fact that as A increases, as the rotation of the black hole gets larger, the modes approach the real axis. They're getting closer and closer to the real axis. This has consequences, as I'll explain later on. And these are for different values of L. These are points, by the way. They're just so close to each other that they look like lines, but they are discrete points. Just for different values of L, from 10 to 180, n equals 10, n equals minus 2. And you can do it for different values of M and L, and so on. Okay, so this is an exact calculation of Poisson modes in Kerr. And as I said before, it has applications. The Poisson modes have got applications for the late time stage of a gravitational waveform whenever you've got a black hole in spiral for any mass ratio, not just for an extreme mass ratio in spiral. So indeed, LIGO, in the force detection that they did, so this is, they modeled the late stage of the gravitational waveform. They could see, they look at the waveform and they say, okay, it's oscillating with a certain frequency. That would correspond to the real part of your quasi-normal mode, of your dominant quasi-normal mode frequency. The imaginary part tells you the decay rate of your field, of your gravitational field.
So is that a plot of data or just a representation? You say numerical
This
relativity.
is t. That is as a function of time. Or
No,
this
no,
is
is that a real plot or is it just a representation?
this is the numerical relativity Rickenstock template. So I think so. There's an overlapping between the prediction for numerical relativity and Rickenstock template.
What I mean is, LIGO will give me that graph from experiment.
Numerical relativity will give you that, and LIGO, after a lot of data analysis processing, will give you that line.
It looks like the one from the PRM paper.
Yeah. This is literally.
Yeah, and why does it go left? Why didn't you have it go left?
Well, you have to ask LIGO. They publish it.
Sorry, what is
How
it?
many quasi-normal modes?
Okay, so good question. So here's where the merger is. After the merger, you can approximate your space-time as your remnant black hole, Kerr black hole, plus a gravitational perturbation. Okay. It is not known exactly from which period you can do that, and there's a lot of data analysis processing and a lot of discussions. You can look at it in the archive of how many quasi modes you can detect. You can see. Okay, there is many groups having constant arguments about this. I'm not really going to get into this, but in the paper by LIGO, what they did say is, we look. I mean, the signal-to-noise ratio for what LIGO did is not good to do proper science with at this stage, at the ring-down stage. But what they did say is, well, our frequency in the oscillation, I think they just looked at one cycle, and the decay rate, it fits within the theoretical prediction of your dominant quasi-normal mode. That's all they could do. So LISA will have a much better signal-to-noise ratio certainly for extreme mass radiation files, for the ring down, and so we hope that we'll be able to do really proper science with LISA. We'll be able to hopefully detect different quasi-normal modes, and with that you can test the Kerr hypothesis, see what really is the remnant object that you've got.
Do it in 12 years.
Yeah,
How many
it'll
years?
go by faster than you think.
12 years. And
So this is a black hole merger, right?
Yeah.
And typically, it would be that one of the black holes could be much, much heavier than the other. And if they're not, if they're roughly the same, what kind of remark can you make about that?
Yeah, well, this is so in the extremes ratio, LIGO does not, the frequencies are too low for LIGO to detect them. They're going to be the sources of LISA. LIGO is detecting equal mass ratio up to intermediate mass ratio.
Okay.
So this is not extreme mass ratio.
Yeah. So this is the best experimental result we will have for these quasi-normal modes, in the sense that some other physical process which involves a black hole but not a merger is too weak to hope to detect.
Without a merger, you should.
I mean, these very energetic things happening, which are, happening in the vicinity of black holes.
Well, they're involving matter. Which things? Well, yeah, I think you're involving matter now in the accretion distance one. So.
Well, I think if you find a black hole merger nearby, Charles, I think you'd be a look.
Yeah.
You should put strong
But they run up. Yeah. But yeah. Interesting.
Yeah.
They couldn't speed up LISA, could they?
I think it's already 2 years. It was only planned. It's since a month ago. ESA announced that it's now planned, and I think it's already 2 years earlier than things are going very, or earlier than it was envisaged. We'll see. It's not going to be an order of magnitude. Maybe we can squeeze in a couple of years. Okay, so that's the waveform and quantum modes. Now we're going to look at unstable modes. So you were asking me before about modes in the upper plane. So now I'll be talking a little bit about the upper plane. So this about unstable modes, modes in the upper plane. Are there any? Well, that's been shown analytically with mathematical work that there are none in the case of Kerr, subextremal Kerr, or extremal Kerr. Subextremal was Bernard-White in 1989, and the case of extremal Rita Teixeira da Costa in 2020. However, it was shown by Stefan Azaretakis in 2010 that if you look at the event horizon of extremal Kerr, derivatives of the field which are perpendicular to the horizon, they grow in time. It's the so-called Azaretakis instability. Now, he could not determine the growth, and he only did for the axisymmetric perturbations. Now, how could there be an instability if there are no unstable modes? So that comes about due to some insight of results that Steve Date-Byler got in 1980, which is, before when I showed you the quasimal modes, and I said, look at the value of A, as the rotation increases, these quasimal modes are getting closer and closer to the real axis. In fact, as you approach the real axis, the quasimal modes pile up and reach the real axis. So this is an actual numerical calculation by a master student of mine in Brazil, Luis Longo, and in Kerr, as we approach extremal Kerr. So what is this? This is a logarithm of the Vronskin. Whenever the Vronskin is equal to 0, you've got a quasimal mode. So the log of the Vronskin is minus infinity. This is a numerical calculation, so all these depths here are where the quasimal modes lie. And these are the complex frequency plane. So this is at A equals 0.95, highly rotating, but not extremal. So this depth here is where the quasimal modes lie. You can see how they're getting close to this particular value of the frequency. Now I'm going to increase the frequency. Sorry, the angular momentum of the black hole. Now it's 0.99. And the quantum modes are getting closer and closer to each other, closer and closer to the real axis, closer and closer to this value in the real axis. And they're teaming up with poles of the Vronskin, in fact, which are totally transmitted modes, in such a way that at A equals M, this is exactly extremal Kerr. This is not extremely close to extremality. This is exactly at extremality. There is a branch cut. There's a discontinuity stemming from this frequency. So a branch cut has been formed in extremal Kerr.
I didn't understand one thing. The Vronskin being 0, why does that be a signal of quasi-number?
So the quasimal modes are poles of the green function modes. The green function modes are you multiply two homogeneous solutions and you divide them by the Vronskin of those solutions. When the Vronskin is equal to 0, that will give you divergence in the modes.
Yeah, I mean, it'll mean that the two independent solutions are not independent anymore.
That's right.
Yeah.
That's right. That's right.
Can you not analyze extremal Kerr on its own? There should be some simplifications that occur there.
Yeah. We did, this is a calculation directly in extremal Kerr, and that's a numerical calculation, and with collaborators, Sam Gran and Peter Zimmerman, we did an analysis directly in extremal Kerr. This is not numerics, but an analysis, and we showed that indeed the transversal derivatives of the green function perpendicular to the horizon, they grow in time along the event horizon. So that's the advanced time, retarded time, the time coordinate or along V increases as you move towards I plus along the event horizon. The more derivatives you take, the faster it diverges. The derivatives diverge.
Where did S come from?
So that's coming from the new branch cut.
Oh, I see. And the half is a funny thing there.
The half is a funny thing. can't remember right now how it arises, but it's arises.
I'm sorry, what is this? Is this an integer? Or?
So n is the number of the derivatives that you take. So when it, s is the value of is the spin of the field.
What's the spin?
Yeah. So spin 0 for scalar, spin 1/2 for fermion, spin 1 for max, spin 2 for gravitational perturbations. So indeed, this comes from the new branch code, which was not there for subextremal Kerr. And in fact, we did this for non-axisymmetric modes, and this dominates over the instability that our attack has found. So we found the leading instability of extremal Kerr, of the horizon of extremal Kerr.
So what is the instability physically? Is it that it's losing its rotation or something? It doesn't want to say extreme.
Well, okay, so probably an object trying to go through an extremal Kerr is going to suffer serious tidal disruption.
Serious what disruption?
Tidal
Oh, yeah.
disruptions.
But this is clearly important because it's there.
Big enough for big going through a Schwarzschild event arises some kind of disruption.
Absolutely, yeah.
Depends on the size of the object.
Yeah, well, this will be totally. But you, I mean, this is note also that this is a late times. So this is divergent as v goes to infinity. So not at your finite times.
So it's not clear what the instability is what you're saying.
Well, at late times, v goes to infinity will suffer infinite tidal disruption if you try to cross it. This is crossing the event. This is the event horizon, of course, not. We're not at the curvature singularity.
Say yes then.
But is a black hole itself unstable? Is a black hole break into smaller things?
Transversal derivatives of the field will, on the horizon, as time goes to infinity, will diverge. You can
They must,
call
it
it.
must be indicating something like that, right? Because the black hole is feeding energy into these holes.
Yeah.
There's
So,
sources there.
so you can see what happens in sub-extremal Kerr, but near extremal Kerr. There is the field grows near the horizon. It picks up. There's a transient instability. So it really grows, it really absorbs rotational energy. This comes from superradiance and the Yerger region.
But this is all classical, so
All these are
black
classical.
hole lose energy, but the area can't put it.
No, the area goes up, but it loses rotational energy, but it loses mass
Yeah, okay.
in such a way that.
There's no back reaction, so you can't really say what's going on.
Yeah. Okay, so that's. How am I doing for time?
You just keep going. So you
Yeah. Okay. Because I'm only halfway through it. Okay, so the next one is the Cauchy horizon. Okay, so that's a whole different setting, but still related to unstable modes and quasi-normal modes and so on. Okay, so what do we have here? So now we're going to Kerr-Neumann de Sitter. So we've got Kerr, we add electrical charge that makes it Kerr-Neumann, and we put it in a universe with a positive cosmological constant. So lambda is positive, we've got 4 parameters to describe the black hole. The Penrose diagram looks the same. The only difference is now what we call future null-infinity. It's now the cosmological horizon. Now, okay, and we've got 3 horizons: the Cauchy horizon, the event horizon, and the cosmological horizon. Okay, So now we're going to look at what's happening inside the black hole. So what happens now, I've extended that kind of diagram to the left as well, gives the maximum analytic extension. So what have we got here? You choose an initial data surface, and you take your maximal Cauchy development of that surface. You put your value for your field on that surface, value for the derivatives, transversal derivative of the normal derivative of the field on that surface, and you evolve that. You use your retargeting function to evolve the field to the future. So you can determine the value of the field anywhere within that maximal Cauchy development. Good. What's not good is if your spacetime goes beyond that. So that means that you, at some initial time, you know your field everywhere in your space. You know your field. You know the derivative of the field, and yet you cannot predict the spacetime beyond some point. That point is the Cauchy horizon. Okay, that's what the Cauchy horizon. That's why it's called the Cauchy horizon, because the Cauchy value problem is no longer well posed. You just don't know what happens beyond that. There's no unique smooth extension beyond that. Your initial data does not determine what your spacetime is beyond that. Okay, so you can say the general relativity ceases to be a predictable beyond that. So that's troublesome. And that prompted Roger Penrose to come up with strong cosmic censorship hypothesis. So there's different versions of it. I've just picked this one. It says that the maximal Cauchy development via Einstein equations of some generic initial data is inextendable. Okay, so you cannot extend your space-time beyond your maximal Cauchy development. There are many tricky bits here. Is what is the level of regularity of your field on that surface? That's a tricky bit. And there's different formulations depending on the level of regularity that you ask for. And it depends on whether you talk to a physicist or you talk to a mathematician.
So can you just go back one slide for, I just want to understand. Now, if I send the cosmological you have two extra parameters here. I want to disentangle them a little bit. If I send the cosmological constant
Yes,
to
yes,
0,
yes,
and I send the charge to 0,
yes.
what's
Same issue.
Okay.
Same issue. So the Cauchy, the Penrose diagram is the same. So the same issue with strong cosmic censorship arises in Kerr. Now, we'll rescue it, as I will show you in a second. In Kerr, we'll rescue it, and in other places it will be problematic, so I'll show you in a second.
What do you mean? So you're saying that you have a Cauchy horizon in Kerr?
Yeah.
Where's the Cauchy horizon?
It's the same. Penrose diagram is the same. The only difference is that this is no longer a cosmological horizon, it's a future null infinity.
Okay.
But the causal structure is exactly the same Cauchy horizon, same singularity, if you do an analytic extension, not a smooth extension. Same black hole exterior. Penrose diagram looks exactly the same, just now this is a cosmological horizon instead of. So same issue, doesn't matter. Kerr, Neumann, that doesn't matter. Same issue here, and so on, and here. Okay, so what can we do with this? If that's really the case, that general relativity ceases to be predictable inside black holes. Well, remember Kerr, Neumann, they're all exact solutions of isolated black holes. We need to perturb with these fields. So does the Cauchy horizon survive under field perturbations? So cartoonistically, what happens whenever you include field perturbations? Does the Cauchy horizon become an irregular hypersurface or not? If it becomes an irregular hypersurface, there could be a curvature singularity, and so maybe an observer going into the black hole will crash to its future will crash into into that hypersurface, that singular curvature hypersurface, just like it would happen in Schwarzschild. Even though it crashes, it looks more dramatic from a biological point of view. It looks nicer from a philosophical point of view. Okay, the space-time remains, general relativity remains a predictive theory all the way. That's where the space-time ends. Okay, so from as biological beings will be sad, as philosophical beings will be happy. So it's a hypothesis, we need to verify it, so let's look at perturbations. Okay, so the question is, and this has been shown mathematically, that's what really matters. The quantum modes that we did before, we were looking at scattering outside the black hole. Okay, so these quantum modes are scattering outside the black hole, but part of them are transmitted through the event horizon, and they reach the Cauchy horizon. So whenever they reach the Cauchy horizon, are they strong enough? Is the field strong enough to destroy, to make the Cauchy horizon irregular, or not? Okay, so some mathematicians, Peter Hinz and Bajci, can't remember his first name, showed that in the case of asymptotically de Sitter spacetimes, the quantity that really matters is this beta quantity. So what is this beta quantity? This beta quantity tells you is the spectral gap, which is how far from the real axis is the highest lying quantum mode. Okay? And then you divide it by kappa minus, by the surface gravity of the Cauchy horizon. So basically, the smaller beta is, the slower the field decays, the larger it will be when it reaches the Cauchy horizon, and so the higher are the chances that it will destroy the Cauchy horizon. So if beta is less than 1/2, it will destroy the Cauchy horizon. But if beta is larger than 1/2, the field will be too weak to destroy the Cauchy horizon, and the Cauchy horizon will be regular, it will remain. What do I mean mathematically? What I mean is that the stress energy tensor for the field is locally integrable, and so there exist weak solutions to Einstein equations, which is what mathematicians care about. They care about weak solutions. Okay, integrating against some test function, your Einstein equations. Okay, so the quantity beta being larger than 1/2 or not, how close to the real axis is the highest lying quantum mode? That's the crucial thing. If beta is larger than 1/2, we're doomed. Or strong cosmic censorship is doomed. If beta is less than 1/2, it's saved. Okay, so people have done some analysis, some different investigations. In the case of Kerr, de Sitter, and in the case of Rajastrom, strong cosmic censorship prevails. Okay, so Kerr de Sitter, Rajastrom is just electrical charge, zero cosmological constant. The problem arises whenever we include a charge to the black hole and it's still asymptotically de Sitter. So that's Rajastrom de Sitter. Okay, so spherically symmetric, electrically charged, asymptotically de Sitter. In that case, it's been shown numerically by Vitor Cardoso and collaborators that beta can be larger than 1/2. So there is violation of strong cosmic censorship. I should say, because I think you're interested, but I'm not presenting this work here because I'm not doing quantum field theory and co-spacetime in the talk here. I will do it on Tuesday, but not in today's talk. People, my colleagues Stefan Hans and Jonathan Tan in Leipzig and Robert Bobwold in Chicago showed that whenever one includes quantum fields, they save cosmic censorship in Rajastrom de Sitter. What about in the rotating case? Rajastrom is spherically symmetric, all black holes are rotating. What about the case of Kerr, Neumann, Sitter? So, PhD student of mine, Cássio Marinho in Brazil, did a numerical calculation of beta in Kerr, Neumann, Sitter. So beta equal 1/2 is here. So Beta larger than 1/2 means the Cauchy-Riemann is stable, so violation of strong cosmic censorship. Below the line, there is preservation of strong cosmic censorship. So what are the different plots here? Well, there's A equals 0, non-rotating case, and the rotating case. And also we've done this for spin 0 and spin 1/2. So let's forget the non-rotating case. Let's look at the rotating case. That's more interesting. That's the orange lines. So the continuous orange line is scalar field. The dashed orange line is the Fermion field. We want, for violation of strong cosmic censorship, we want that no field is strong enough to destroy the horizon. So we want beta larger than 1/2 for all fields. So this small region here of parameter space is where both spin 0 and spin 1/2 fields would violate strong cosmic censorship. So it's a small region of parameter space. It is unphysical because it's very, very close to extremality and for a large cosmological constant, but it is a region of non-zero measure. Okay, there is a region of parameter space of non-zero measure in which you have violation of strong cosmic censorship for rotating black holes, classically. And quantum mechanically, people have not looking into that, but there's no results.
Can you say again exactly what you mean by violation of strong cosmic?
Yeah, so I mean that the strange energy tensor for scalar fields and for fermions is non-locally square integral. So that's exactly what I mean.
It's not locally squared.
Locally square.
Locally
square.
Locally squared.
Yeah.
It's not locally square integral, then you have a violation. You're saying you have a violation.
Yeah, so it wouldn't admit weak. Einstein equations don't admit weak solutions. Okay, so that's the section 3, black hole stability, and now I'll talk about some quantum results. First of all, about communication, and although it still uses retarded green function, and then entanglement harvesting, which uses Feynman green function. Okay, so what's the physical setup? So by the way, this is going to be Schwarzschild now, no longer in Kerr, this is Schwarzschild. So we've got two quantum particle detectors. We're quantizing the field now, and we've got two quantum particle detectors, Alice and Bob. The black hole is here, the event horizon is here. This is Schwarzschild now, the event horizon 2m. And these are your two particle detectors, following two different word lines, XA and XB. So we want to look at communication between the two detectors, passing information through the field between the two detectors. So how do we model the two detectors? Well, we use the so-called on-road-away detector. So there's a very simple toy model for the detector. There's the Hamiltonian for the detector. You've got some energy gap given by omega, an excited state for the detector and a ground state for the detector. This both for Alice and for Bob. You've got your interaction Hamiltonian between the detector and the field. So you've got your coupling constant lambda, a switching function whenever you switch on the detector, whenever you switch off. In here, we're just going to take sharp switching on and switching off. Your monopole operator for the detector, and then your quantum field. So that's the interaction Hamiltonian. And for the initial quantum state of the system, Alice, Bob, and the field, we have this combination for the Alice's initial state. Bob is in the ground state. You've got some coefficients, theta, beta, zeta, and so on here, and the field is in some state. Doesn't really matter. We've got the time evolution operator, and we use a Dyson series, so we expand for small coupling parameter lambda. So if we look at the final state of Bob, so this is particularly for Bob, so we trace over Alice and the field after we evolve the initial state of the system and expand in the perturbation coupling constant lambda. You find these three contributions. This just involves lambda b, the coupling of beta of Bob, lambda b coupling of Bob. This is for the ground state. This is for the excited state. This would be, remember, Bob starts in a ground state. This is excitation probability independent of A, so this has nothing to do with communication with Alice. Communication with Alice comes here, where lambda A appears. Okay, so this is excited Bob, and so this is the leading order signaling contribution. Now, if we look at the channel capacity, so this is the optimal success probability of random bit transmission from Alice to Bob. So you've got 1/2, which is just random, just 50% chances of getting.
I missed what zeta was.
Zeta is the initial. It's related to the initial state of Alice. So the deviation from just a total random guess of 50% chances of guessing is given by lambda A, lambda B times C2 and D2. So these are, C2 and D2 are really important quantities here. So how do we calculate them? Well, it's a double Warline integral of the retargeting function where the arguments are Alice and the Warline of Alice and the Warline of Bob, modulated by the energy gap of Alice and of Bob. So what you really need to calculate is the green function and integrate it a twice double Warline integration. And D2 is just trivially obtained from C2. So C2 and D2, different from 0, it tells you about improvement in the communication between Alice and Bob. So we know, how does the communication happen? Well, we're all experts now in propagation, wave propagation, black hole spacetimes. So remember, we've got different contributions. There's the direct wavefront contribution, and then there's the orbiting null geodesics, the one that orbits around the black hole. And we also have the backscattering of tails, the fact that the Hadamard bitensor V is not equal to 0. So all these contributions, they give you, they contribute to the Warline integrals and so to the channel capacity. So this is a numerical calculation of the channel capacity, C2 plus D2. So this is anything that's non-zero here gives you a better than 50% chance of guessing the bit, or the bit, Bob guessing the bit that Alice has sent it through the field. So this is just the equator of Schwarzschild. On the vertical axis, there's the channel capacity. And this is where where Alice sits. And there's a divergence. There's a divergence where Alice, if Alice sat exactly the same place where Bob sits, it would be a divergence. It's hard to see here, but there's ripples. There's some oscillations, and these ripples come from the orbiting null geodesics. And the divergence obviously comes from the direct part, u delta sigma. So the dominant term is the direct part, the u delta sigma, and the backscattering and the orbiting null geodesics gives you some modulation to the channel capacity throughout. By the way, there's a divergence of caustics. There's a divergence in caustics which can't. I've got another plot that shows it, but I didn't show it here. Okay, so that's the channel capacity. That's for static detectors. A curious case where there's an infalling detector. So now Alice is falling into the black hole. And in that case, as she's getting close to the black hole, red is the dashed is the non-direct part, and continuous is the direct part. So the important thing here is that the dashed is larger than the non-dashed, and she gets close to the black hole. So basically, the communication from Alice to Bob is larger from non-direct orbiting of geodesics than from direct geodesics between Alice and Bob. So that's an interesting feature that happens when you've got orbiting null geodesics and when Alice is getting close to the event horizon.
Okay, are you summing over indirect ones, or what is going on there? Because that's strange. It's strange that the communication is more.
Yeah, we did look a lot into it.
Are you summing over all indirect?
Oh, I think you just see, I think there's just the secondary ones. No, so even just the secondary one gives you a larger contribution. I think the tertiary one, I think that gets really low.
So the secondary one
The secondary,
is giving a better communication.
yeah.
It's very strange.
Is it a lensing effect? Is it some kind of like magnification due to lensing?
Yeah, so why is it?
It's just very strange.
I remember we looked into it and were happy that this was happening. I just wonder what it has to do. So I'm going to show around something that might be related to this. So the singularity structure changes. Like I said before, it changes from delta sigma to a PV, to a principal value of 1 over sigma. I'll show you really interesting things that happen now due to that. And I wonder if that, it must have to do with this, because that's really the crucial difference between the direct null geodesic and the second null geodesic, that the delta sigma becomes a PV, principal value. So it has to do with this. So I'll show you now more in detail what happens in a very similar scenario, but it's different. Okay, and that's the last one. That's the entanglement harvesting. So what's this? So now we still have Alice and Bob moving in some Warlands in Schwarzschild spacetime. We just changed the switching functions. Now it's a smooth Gaussian distribution for both. Now both of them in the ground state, and the field, the quantum state of the field now plays a role. So rho phi, we're going to choose here. So this is the field, the state of the field in a black hole space-time. So there's different quantum states. We're choosing the Unruh state. So the Unruh state models the state of the field near an evaporating black hole, evaporating via the emission of Hawking radiation. So it really is the most astrophysically relevant quantum state. So we set the detectors on the ground state and the field on the most astrophysically relevant quantum state. Okay, so a measurement of the entanglement that there is between the two detectors, between Alice and Bob, at the end, after some time t, actually, as t goes to infinity, can be done through the so-called negativity. So that can be shown that the standard quantity for using for measurement entanglement. So what's this? So this is again an expansion in the coupling constant. So the leading order is the maximum between 0 and m minus L. So what are m and L? Well, L is the local noise term. So again, it's a double integral. Now it's the Weidmann function. So I introduced this earlier on. We had the Feynman going function was theta t minus t prime times the Weidmann function. Okay, plus the swap x and x primed. So this contains information about the quantum state of the field. The expectation value of the Vig product of phi in some quantum state psi. In our case, it's the Unruh state. Now, this guy only depends, this is for each detector. So this only involves one detector. D can be either Alice or Bob. So it has there's nothing coming in from the other detector. It's just literally a local noise term coming from a detector in itself. And it's the same for Alice and Bob. The interesting bit is the correlating term. So this one involved two detectors. So the two switching functions for Alice and for Bob, and the two Warr lines for Alice and Bob. So again, it's a double Warr line integral involving the Weidmann function with the Warr lines of Alice and Bob.
Isn't the Weidmann function more unphysical in this setting?
Unphysical.
Yeah. It's not retarded and it's not the Feynman one, so.
No, but it's I mean it's Feynman-ish.
No,
It's the Feynman whenever t is larger than t prime, it's Weidmann.
yes,
Blunt?
it's not time altered, it's the heat.
Right.
which is.
So I think because I think we must have so I can't remember right now, but what we must have done. It's quite likely that one uses the Feynman and then one swaps the two depending on the theta t minus t prime, the theta t prime minus t. That's probably what gives rise to the two different terms here. Okay, so the correlating term is the really interesting one. Whenever n is larger than L, then the correlation term is larger than the local noise, and you've got entanglement. Now, I'm going to distinguish between two different things. One is well, if you split it into the real part and imaginary part, m plus or m minus. M minus is just the retarded, it's proportional to the retarded Green function. And so that does not depend on the quantum state of the field. So it just corresponds to the direct communication like we had before in the previous section. M plus is the anti-commutator, so that does depend on the quantum state of the field. So what that really tells you about is not direct communication between Alice and Bob, true. It's literally the detectors are extracting entanglement that's pre-existing in the field. Okay, it's not communication from Alice to Bob, but it's entanglement in the field itself. So that's a really, it's particularly interesting to look at M plus specifically. So this is a numerical calculation that I did. Oh, I forgot to include the names here. These are a lot of, I'm particularly bad because a lot of perimeter institutes. So this is Achim Kempf in Perimeter Institute, Robert Johnson, who's now in Sweden, was in PI, my student Joao Caribe, and Martin Martinez, something else, in Perimeter Institute and Waterloo. Okay, Eduardo Martinez, so nothing else, and then fortunately I was missing Eduardo. Okay, so what's this? So let's look at, so this again has lots of interesting things in terms of propagation. Okay, so what's happening here? So first of all, this is similar to the plot of the Green function before, the video of the Green function before. So there's been emission of a null wavefront here. So this is the null wavefront being emitted by some initial point, some initial time at the point here. And these are Alice and Bob. So Alice is going in this direction. Yeah. So this is, we're just they have the same radius, and we're just looking at an angular distance. So gamma here is the angular separation between Alice and Bob, between the 2 points. So the wavefront is just propagating like before. It's in this direction, it's going to flat space-time, and in this direction, it's just going to start orbiting around the black hole. And here we're plotting. Okay, what are we plotting here? We're calculating M, which is the blue. Okay, so it's not very clear in here, but the blue line is here. That's the outermost layer. The outermost curve is M. The horizontal line is the noise. So for negativity to be non-zero, so for entanglement, for the final state of bond to be an entangled state, we want it's only going to be wherever the outermost envelope is larger than the horizontal line. So in here there's entanglement, and in here there's entanglement, but in between there isn't. For values of gamma, in between there isn't. You cannot see the colors here, but there's an M plus and M minus. Whenever M plus is larger, we've got entanglement harvesting. The detectors are harvesting entanglement from the field itself. It's not through communication. What's happening here, you can't really see it, but the green line is dominant. So it's just communication. It's just communication. Now, as we get close, so now we're getting close. These points are getting close to the caustic. So this point here is going to be a caustic point. It's where the wavefront coming from both sides are going to meet. Okay, so you can see how now the peaks are getting closer and closer in gamma, because now, sorry, gamma equals pi is here, so this is the caustic, gamma equals pi is here, so getting closer and closer to the caustic. And as they get, so in here, okay, that was very good, that was well done. In here, okay, it's just gone a little bit after the caustic, but in here, M plus dominates, so M plus is here. So there is harvesting of entanglement by the detectors from the field at caustic points. And this comes from the principal value distribution, the 1 over sigma, the change in the singularity structure of the green function. And then, well, now they continue and they go back to normality, so to speak. So this is again no harvesting and so on. So this happens. And then, of course, the magnitude of the field, as time goes by, the magnitude of the field decreases, so that then it's always lower than the noise term. But at the first caustic, it's larger than the noise term, and
Before the first caustic, it dropped below the noise term. So was there any significance in that?
yeah, so that's because that's flat space-time-ish. So yes, exactly. So in here, that's right. So in here, that's the field as it moves away, it's just losing magnitude. And if there was no caustics, if the field didn't pile up again, it would just get diffused and it would just be below the line. It's the fact that the field meets from the two sides, piles up again, it peaks up again at the caustic that allows for the resurgence of entanglement to happen and harvesting to take place. Okay, so that's the last calculation and application of green functions which I wanted to present. So just summing up, green functions are crucial objects. Classically, we've looked at the calculation of the self force. It gives geometrical insight in terms of wave propagation, backscattering, orbiting null geodesics. It can serve to model the ringdown. This is for inspirals for any mass ratio, including LIGO. Looking at the stability properties, the classical stability properties in terms of unstable modes. And for quantum physics, we looked at the contribution of the retarded green function to communication, and it can be larger from the orbiting null geodesics and indirect null geodesics in the case of an observer, a detector crossing through the horizon. There can be entanglement harvesting happening near caustics. And then future things to look at, or extra things that one could look at, is higher order perturbations. Now, that's actually, I've only looked at linear field perturbations so far. If you look at higher order perturbations, the equation is going to be the same. It's just that the source now is going to be, the source of second order field is going to be sourced by the first order perturbations. But the equation is the same, so you still want your green function. It's still very important. Now you have to integrate it with your convoluted, with your different source, which is it comes in from the first order calculation. That's actually necessary for LISA. LISA requires second order self force calculations in Kerr. So people are currently doing this, led by Barry Wardell is one of the leaders of this in UCD, and Niels Warburton as well. So that's useful for the self force and also for ringdown. There's been a lot of bouncing of archive papers about the ringdown, whether one can see higher order modes and higher order modes in perturbation theory in numerical relativity, and whether LISA will be able to see any of those. So LISA should be able to look at higher order terms in perturbation theory. And finally, in terms of quantum effects, well, if you look at the Feynman function, you can then calculate the stress energy, the quantum expectation value, renormalized expectation value of the quantum stress energy tensor when the field is in some quantum field, in some quantum state. And then that gives you an idea of what the semi-classical effects are. So I'll be talking about that in the journal club on Tuesday. So thank you very much. Any questions?
That's very interesting. But I asked so many questions already. I won't ask any more.
I'll also be here for the whole until the end of next week.
It's a great talk.
Thank you.
Perturbation theory calculations. How do you estimate the effect of back reaction? So in the merger of the black holes, the self force they compute presumably for the ratio of the masses.
Yeah, so second order, so people are looking at second order. That would be second order in the ratio of the masses.
So this is only a fixed Kerr metric.
Yeah, so you can look at what happens to the massive black hole at the center. The change in that is still negligible at this order. If you went, but at some stage it will of course become relevant. But at this order it's still non-relevant.
But it's ways of estimating.
Sorry? It's been
You know how to
estimated.
estimate.
Yeah.
Yeah.
Yeah. I don't know whether you can check in the chat if there's in the chat.
Thank you very much. Just,
Yeah.
correct, oh, how good. And good is singular.
Yeah. Oh, I see. I did. Yeah.
And you don't need an explanation.
Explanation like this. Emojis are everywhere. These are old emojis, Charles. You shouldn't drop the old emojis. What's the emphasis?
You realise that all the time that Marc was talking, it says talking danger one part. Yeah.
Yeah, that shows they should change that. We should change that on the website somewhere. Thank you very much.
Thank you.
Yes.
So just leave this open a minute.
Yeah, all right.
Yeah, you can stop the recording.